Hi, chemistry students. This is your lesson on the history of the atomic model, which is from our Unit 5 and Lesson 1, and you should have some notes that are for Lesson 1, History of the Atomic Model. It's a chart that you should be filling in as we go along. So here we go. Now with this recording, you may want to pause a little bit more frequently, but I will give you a cue as to when you should pause as you're filling in your chart. So this is Unit 5, Lesson 1, History of the Atomic Model. So what this lesson is about is you take for granted the current atomic model, right? We talked about that in the last unit. You got the nucleus in the middle, you got electrons around the outside, but where did this current model come from? It's really not that old. So we're going to be talking about the specific men that you're seeing here, okay, as they think about the fundamental nature of the universe. And these are the people that the Virginia SOL wants you to know about. So here we go. Starting with Democritus. The first person to propose atoms was a philosopher named Democritus around 450 BC. However, he was a philosopher, not a scientist. You might want to write down that in Greek, atom means not able to be cut. And he had the idea for the atom when he was spending some time on a beach in Greece, looking out at the ocean, looking out at the sand, and realizing that although the sand looks like one thing, it's actually made up of many little teeny parts of particles. And he thought, well, maybe matter is like that. I can't really see the particles, but if I looked a little more closely, I would. So he first proposed it, but it was just theoretical. He didn't base it on any sort of experiment. So to Democritus, atoms were small, hard particles that were all made of the same material, but were different shapes and sizes. Atoms were infinite in number and always moving and capable of joining together. So in your chart, you should check off indivisible with Greek solid sphere. Now, this sounded like a really good idea, but Democritus wasn't a very well-respected philosopher. Much more well-respected was this guy named Aristotle and his mentor Plato, who you may have heard of. They favored the idea that everything was made up of four elements: earth, fire, air, and water. And even though, again, they did not base their idea on any sort of experimental finding, they were much more respected. And so for about 2,000 years, that idea of the atom that Democritus proposed didn't really go anywhere. So that brings us to the next box, which is the solid sphere model that was actually based on experimental data. And the guy in this picture here is a guy named John Dalton. You should write down 1803 and that he was father of the modern atomic theory. Leave yourself some space though. You don't need to copy this, but essentially he performed a lot of experiments. He was a school teacher, but he was also an amateur scientist who, with his school teacher salary, liked to experiment and see if he could find things out about nature. So he performed a series of experiments on mixtures of gases to determine what effect properties of the individual gases had on the properties of the mixture as a whole. While trying to explain the results of those experiments, Dalton developed the hypothesis that the size of the particles making up the different gases must be different. So you need to check off, he again thought atoms were indivisible, did not have parts, but he had four basic principles of the atomic theory that you need to write down, small, in the space for Dalton. Number one, you again may want to pause the video. Number one, matter is made up of atoms, and atoms are indivisible and indestructible. Okay, now that's not really true, but at the time, it matched his experiments, and it was certainly a step in the right direction away from Aristotle. He also said all atoms of a given element are identical in mass and properties. Again, what he could measure, it seemed that way. He didn't know about isotopes. They certainly had the same number of protons, but he didn't know about protons. So that was number two. So a good step in the right direction, but not quite right. The last two principles, though, were pretty much on. He said compounds are formed by the combination of two or more different kinds of atoms. So like water was formed from hydrogen and oxygen, for example, and that's pretty much true. He also said a chemical reaction is the rearrangement of atoms, and that matter is neither created nor destroyed. So again, Very good idea in terms of being pretty much spot on. But again, he still didn't realize they had parts. So in your checklist for next to Dalton, you should put indivisible. Okay, so when do we actually start to see parts of the atom? Well, that didn't happen until 1897 with Thompson's plum pudding model. You can check electron in your chart, but there are two things, and they're underlined here, that you need to make sure that you remember about his experiment and his model. Thompson studied the passage of an electric current through a gas, and his experiment was in something called a cathode ray tube. It looks like this, okay? As the current passed through the gas, it gave off negatively charged particles that he called electrons. And that caused him to realize, like, where did these electrons come from? Well, they must have come from the gas. They must have come from the atoms of gas. Therefore, the atoms of gas must have parts. So he proposed this model, and you can draw it, that essentially was like what he's thought of as plum pudding. We sometimes now call it chocolate chip cookie. In other words, you have the cookie part was all positive, and then you have these little negative electrons that are sort of like the chips that in the cathode ray tube were kind of being knocked off and were causing this ray to form. So it was called the plum pudding model or the chocolate chip cookie model. We know this isn't what an atom looks like, but this is the first time we realized that atoms were not indivisible. That's why you'll check off electron on your chart. So again, just to go over this, in the 1890s, first time we saw a subatomic particle, Thompson concluded that the negative charges came from within the atom. He discovered a particle much smaller than an atom with a charge. He discovered the electron. Okay. So again, after he realized there were negative parts, protons were pretty easily confirmed. If an atom is neutral, it has to have both negative and positive parts. And again, here's another picture of a cathode ray tube. All right, so this next one, you'll notice all the checklist is blocked off. Virginia SOL wants you to know this man's name. His name is Robert Milliken. He did a very famous experiment, and you should write this down, called the oil drop experiment in 1910. And this is kind of what it looked like. But essentially what he was able to do from this apparatus, and he had sort of two charged plates, and he was able to actually have the electrons kind of attached to oil drops that fell at a certain rate. And by doing some mathematical calculations, he was able to determine the charge on an electron. So that further quantified that electron was a real thing, and he was able to actually say each electron had a particular charge. So you want to write down Robert Milliken, charge on the electron, oil drop experiment. Okay. So now we're going to get closer to the more modern version that you've been taught in school since probably the 4th grade. It was proposed by an English physicist named Ernest Rutherford, and it was based on a very, very famous experiment called the gold foil experiment. You may want to stop the video and sketch this a little bit, but I'm going to describe it. So what he did was, inside of a lead box, he put a radioactive sample. And that radioactive sample gave off something called an alpha particle. An alpha particle is essentially 2 protons and 2 neutrons, kind of like a helium nucleus. Some radioactive materials give those off. Alpha particles can't go through lead, though, so he put this radioactive source in a lead box and essentially put one hole, so he made kind of an alpha particle gun. He aimed that gun at a very thin piece of gold foil, and around the gold foil he had a radiation detector, so he could see what happened to the radioactive particles. Now he was kind of expecting that the radioactive particles were going to be so powerful that they would just go right through and there wouldn't be any disruption. But essentially what happened, and it took him 2 years then to figure out why, is that while most of them went through, you can see this red line, most of them went through, a few, not many, a few were diverted. They sort of went diagonal, and a very few didn't actually make it through. They bounced back. And he had to think, well, how do I explain this? If they're so powerful, why are they being diverted and why are they bouncing back? One important thing you should realize about an alpha particle, since it's 2 protons and 2 neutrons, is it's positively charged. And you have to remember that things that are like charged tend to repel each other. So what did he come up with? Well, he came up with the idea of the nucleus. So this is what he thought. So if you sort of imagine that this is the gold foil, and if the atom essentially has a nucleus with electrons around the outside, but that is mostly empty space. Again, his observations were a few were deflected and a few actually bounced back, about 1 in 20,000. So what he thought was these alpha particles were actually going through because they weren't hitting anything. They were going through empty space, that these atoms were mostly empty space. However, when the alpha particles that are positively charged get close enough to a nucleus, because they're both positively charged, there'll be this diversion, and that happens sometimes. Every once in a while, the alpha particle will be heading straight for a nucleus, and it will be bounced all the way back. So that model, where you have this very teeny positive nucleus and pretty much empty space except for some electrons racing around out here, could explain the results of his experiment. So that was his theory. So next to Rutherford's nuclear model, really important that you put the gold foil experiment, that you check electron and nucleus. This is essentially what he thought it looked like. He had a nucleus with protons and neutrons, and I'll explain when that came into play, but very shortly afterwards. And then the electrons were somewhere out here, okay? But they weren't very massive and they weren't doing very much, and most of the atom was empty space. Very pivotal. Gold foil experiment, electron and nucleus, check those off. So you should write this in your notes under Rutherford. The atom is, he said, based on the gold foil experiment, that the atom is mostly empty space. Most of the mass is in a very small region at the center called the nucleus, which is positively charged. And negatively charged electrons that had almost no mass were outside the nucleus and moved around in this empty space. So our sort of modern basic picture of the atom came into play in the early 1900s. So in 1920, he actually said the positive part, he used the name proton for the first time. He also said there had to be something in there to hold the nucleus together. So he called those neutral particles neutrons, but they weren't actually discovered to be existing until 1932. It was discovered by a student of his named James Chadwick. And I always get 1932 and think about how recent is that picture of the modern model with the nucleus and the electrons on the outside and protons and neutrons and electrons, because my dad was born in 1932 and my dad is still alive. He's 85 years old. So this picture that we've been learning in school is not really that old. And that's kind of cool, I think. All right, so unfortunately, that basic picture we learned is nice, but it's a real simplification. And so some experiments were going on at the same time in physics that would lead to a little bit more sophisticated idea of what the atom looks like. So Max Planck, and you need to write him down, discovered that atoms in a flame could absorb or emit energy in discrete amounts. These discrete amounts of energy were called quantum. Okay, so atoms could absorb energy, and they would also emit energy in very specific amounts. And so a man named Niels Bohr used this idea to have a more sophisticated version of the atom. So Niels Bohr in 1913, shortly after Rutherford had sort of proposed this nuclear model, said, wait, there's some experimental data that seems to indicate what the electrons are doing. He said that atoms emit light of specific wavelengths or colors when they are excited in a flame, like Planck said. He determined that the light came from excited electrons when they lost their energy. And that meant that electrons could only have certain quantized energy amounts. And again, it's because the colors, and we're going to see this in a lab soon, the colors that came off corresponded to specific energies. We'll talk more about that as we go on, but essentially he arranged these electrons so they could only have certain energies. So in your notes you should write what he found out in 1913 and then won a Nobel Prize in 1922 is that each electron is in a specific energy level, and these energy levels he called electron orbits or shells. And you probably drew pictures like this in the 8th grade. And the idea is he thought the electrons were orbiting the nucleus kind of like planets around the sun. They had specific orbits. So just like, fortunately, Mercury doesn't go well anywhere at once in the universe, it stays in an orbit. He said the electrons also stayed in very specific orbits where they possessed a certain amount of energy, so they didn't go crashing into the nucleus in order to stay in those orbits, sort of like planets around the sun. So again, you should check on your notes the Bohr planetary model, because he called these energy levels orbits. Electron, nucleus, and orbit. And the idea was there was a nucleus, but then you had these orbits, and the first orbit held 2 electrons, and the second orbit held 8 electrons, and the next orbit held 8 more electrons. But they were these very specific paths that the electrons had to possess a certain amount of energy so that they would not go crashing into the nucleus. So energy levels. However, this is Bohr as a young man, he wasn't quite right about this. He pictured electrons orbiting like planets orbiting the sun. But very shortly afterwards, other scientists realized that he was wrong, that while electrons do have certain energy levels, they don't orbit like planets. They kind of buzz around like bees in specific areas where they're going to be more likely to be. This is because of a guy named Heisenberg. And you should, under quantum mechanical models, write down the Heisenberg uncertainty principle. And this is what it said. It said, it's impossible to determine the exact location and the momentum or speed of an electron at the same time. So what did that mean? That meant that these orbits don't work well. Very specific orbits, you can't really know exactly where an electron is. And when he did the math, Bohr's idea only worked well for hydrogen atoms. Now, hydrogen atoms only have 1 electron. As you got bigger and bigger and bigger, the math didn't work. Now, we're not going to do the math, but what I want you to realize is that the modern version of today, which was expanded on Bohr's ideas by Edwin Schrödinger, Louis de Broglie, and Werner Heisenberg, they used and derived mathematical expressions to predict the movement and location of the electrons. And so instead of looking like orbits, where the electrons look like were more like clouds. So this is what I want you to write down. Electrons moved in these things called orbitals. They were areas, let's go back. They were areas of probability like clouds versus orbits that were exact paths. So it's kind of a nuance, and it's not actually something that we're not going to do the math, so it probably doesn't matter too much to us except for how we envision the atoms. We've always envisioned them like planets around the sun, and that's not quite right. Instead, the energy levels are not orbits, but they're orbitals. They're like clouds. So electron clouds are not circular orbits, but orbitals of specific energies. They're still energy levels around the nucleus where the electrons will be likely to be found, and they're more like clouds. So for example, here's the nucleus. This is 1 orbital. See how it's kind of, and we're going to talk more about this. This is called a p orbital. And essentially, if an electron has a certain amount of energy, it is probably going to be found somewhere in these lobes here. If it has a different amount of energy, it's going to be this is an s orbital, it's going to be found somewhere in this sphere, but it won't necessarily be orbiting like a planet, it'll just be here somewhere. And the math for this worked much better. So on your chart that you have been filling in, this is what you should have. The Greek was theoretical and said that the atom was indivisible. So did John Dalton, but it was based on experimental work. Thompson's plum pudding gave us the electron, but didn't really tell us where it was. Rutherford's nuclear model gave us both the nucleus with the protons and the neutrons and the electrons around the outside, but not really where around the outside. Bohr's planetary model said, well, they have orbits, they have these specific energies, and so they orbit like planets around a sun. So he proposed energy levels and orbits. And then in the 1920s and even through today, we're looking at more nuanced versions of this and saying, well, they do have certain energies, but those energies don't make orbits, they make more like areas of probability or the electron cloud. So one more time to summarize. The Greek model, first time we had the word atom was the 400 BC. Then we had Dalton's model in 1803, where again he picked up the word atom, but it was based on experiments. And then we had Thompson's model with his cathode ray tube in 1897, where he actually knocked off electrons and realized that the atom had parts. And then we had Rutherford's model with the gold foil, where he proposed the nucleus. It's called the nuclear model. And he said, you had the positive nucleus, but the atom was mostly empty space. And then we had Bohr's model, where he said, okay, let's arrange the electrons. They have certain energies. We know that from Planck's observations, and therefore probably those energies are in these circular orbits. And then we have this sometimes wave model or quantum mechanical wave model, the modern version, which we work on even today, where they're talking about these energy levels are not really circular orbits, they're orbitals, which are really like clouds, areas of probability. So let me come back here. So that is your lecture on the history of the atomic model, and there you go. See you later.